Hello everyone and welcome back to this NPTEL course on aquatic geochemistry. We had been discussing the rubidium, strontium, samarium, neodymium radioactive isotope systems and their applications, especially in understanding natural processes in aquatic systems like weathering, mixing of different sources, and its different kind of applications that we have seen related to understanding of basin, bedrock ages, weathering processes, as well as even ocean current mixing in the global oceans. So, now we are moving to this particular lecture on mixing, and as I have already discussed of the first a little bit on mixing, that in geochemistry we always deal with finding the correct sources. We have to attribute some the processes or whatever we are trying to understand, whether it is coming from different sources, whether they are changing with time or their contributions are changing with time. So, to understand about the processes, we have to deal first with the contributions, and this mixing theory helps us calculate the contributions from the different kinds of sources. So, particular types of equations that we use, and of course, it always uses some kind of elements, either the element ratio or the isotope ratios. So, we in our previous lecture we began with using only the element mixing and how we do the unmixing. Okay. So, if we have two elements plotted in the x axis and y axis, then how we can calculate the fraction of a particular kind of of a particular end member if it is a two end member mixing model. Now, explaining the two end member mixing model is the basis, because based on that we can add on to the complexities, we can add on to the number of end members. If we need more end members, we just need some more tracers. By tracers I mean either the concentrations or the elemental ratios or the isotope ratios. So, given this kind of mixing, we are going to find out how many end members are there, right. So, what happens if you are confused about the number of end members? Okay. So, when you plot, when you are working with a system, for instance, say you are working with a lake. Okay. If you are working with a lake, then you know that what are the hydrological end members. Okay, that can cause change in the water chemistry, because of course, water has some history, water will have its own interactions wherever the water has been draining from. So, if you know that the water entering the lake is coming from say a river or say from the groundwater, so that may be your source A, okay, source A, source B or something. Then there can be some other interactions. For instance, there can be basin, in the basin there can be weathering going on, there can be biotic interactions going on. So, such things can be your source B. Okay. There can be other, there can be some anthropogenic contributions coming, that can be your source C. Okay. So, your number of sources coming to a lake that can cause changes in the chemistry of the lake can be many, okay. But from that we have to select how many we can correctly identify, how many we can correctly separate out from the. For instance, if we have anthropogenic sources. Now, anthropogenic sources can be multiple kind, it can be industrial, it can be agricultural, it can be domestic, municipal, it can be of other kinds as well, it can be traffic waste and some particular kind of waste, so specific kind of waste. Now, if we cannot differentiate between these two, we will not be able to do the source attribution. So, for us to do the source attribution, the first thing that we need to is whether we have a particular tracer that will allow us to do that kind of source attribution. If your traces do not allow you to do that, you will not be able to differentiate between the different sources. Okay. So, the first point is select your source traces. So, once you know that this is a very good, very a very strong tracer that will definitely show me these n members, then we divide the n members. How many n members can we do? For instance, in headwater basins, sometimes it is difficult to differentiate between snow and ice. Sometimes it is difficult to differentiate between snow and rain. So, people combine them, say often people combine the snow with the rain and say it is as precipitation. So, it can be either in the form of rainfall or it can be in the form of snowfall. So, in those cases the two sources get combined as a single source n member. Okay. So, this kind of mixing you have to understand that how many sources you can correctly attribute to. And the data therefore will also share show you how to select. For instance, once your tracer is fixed, okay, and you plot the two kinds of traces. Okay. So, this is your tracer A and this is your tracer B. If it is a 2n member, then generally it will plot between this to differentiate different n members. So, this is my n member A and this is my n member B, because those have very two A and B values, right. So, either this or this. Okay. So, either it is very low on tracer A and very high in tracer B, or very high in both the traces, or very low in both the traces, or very high in both the traces. So, some kind of mixing line, and you will see when you plot your data, that is the mixed samples whose contribution you want to quantify, you will see that the data will lie like this, that is along the mixing line of these two n members. But if it is more sources are coming in, if there are more dominant sources, then how will you know? You will see that the data will form like a triangle. So, you will know that there is another maybe source here, another source C. So, if you find such kind of triangular distribution as compared to a linear distribution, you will know that there will be 2n members or 3n members. If otherwise it is a scatter, so the data is all over the place, you will not be able to do with this 2n member. You have to go for a 3n member mixing model and more complicated kinds of modeling with more tracers and able to differentiate all the 4n members. So, this kind of modeling, you have to select the tracers, you have to plot the data and see whether there is a good correlation between these tracers, and you can see the distribution of the data set. If the distribution is quite linear with the tracers, then you understand, okay, it is a 2n member mixing model. If it is not, it can be possible that it is a 3n member mixing model. Okay. So, 3n member mixing model can also be possible. Okay. So, this is how you come to know by plotting the data. Only if you plot the data you will understand. Sometimes you may not know the n member, you may have no understanding what the third n member could be, but the data could hint could give you a hint of what kind of n member it should be. For instance, this kind of data spread where you have a kind of triangular data spread, you know this n member A, you know this n member B. So, your data will show you that there is another n member which is here, okay, and the n members will plot far off from the mixing line, all right. The n member will not, so it will be n member will lay on the far end of the data spectrum, right. So, your source n members will be here. So, even if you sometimes do not know the third source, by the nature of the plot itself, you will know where it should lie, whether it should lie here, whether it should lie here, whether it should lie here. So, where the third end member would lie, you can just make a guess, you can do some artificial calculations. Artificial calculations means consider this as the end member and try to do the calculation, consider this as the end member and try and do some calculations and see the results. So, moving on to another kind of mixing is the ratio mixing. So, first we saw the element mixing. Now, let us see the ratio mixing. Why are we going to see a ratio? Because often we deal with ratios more accurately than we can deal with simple concentrations. Because ratios, they sometimes are measured more accurately in the instrument rather than the entire concentration. For instance, in the radioactive isotope systems, we always report the ratio. We do not report the 87 rubidium radiogenic concentration. We will report the 87 strontium by 86 strontium isotope ratio. So, isotopes are always reported in terms of ratios. Also, concentrations can sometimes be very difficult to understand. For instance, when you measure a concentration, there can be many additions, subtractions that is finally giving you that particular value. But the ratio of any two elements particular for the process that you are trying to understand may remain the same. For instance, strontium is a very incompatible element, that is, when there is melting going on, strontium will move to the melt phase. Okay. So, the strontium concentration will change as the liquid amount is changing. Okay. As the melt is moving away from the source from where the melt is being generated, the strontium concentration will also be changing. But some other element, if I am trying to check that, so for instance neodymium. Okay. So, neodymium is also that kind of incompatible element. Okay. So, samarium, its parent, and neodymium, they are both compatible in nature and far less incompatible as compared to strontium. So, they will prefer the magma phase, that is the phase from which the melt is being generated, the mantle phase. So, they will remain in the minerals. So, the strontium is to neodymium ratio that may not be changing as much as the strontium concentration is changing. So, therefore, working with the strontium by neodymium ratio will be far more accurate than just using the strontium concentration. So, when I use the strontium isotope ratio, if I am doing a kind of mixing, will this equation be correct if I write that the 87 strontium by 86 strontium of the mix is equal to the fractional contribution from end member A and the fractional contribution multiplied by the end member B? No, that is not correct, because you see here we did not take into account the concentration. So, always when we are talking about isotope ratios, we have to weigh in that mixture with the concentration of the element in each of the end member. That means, in this particular equation, we have to multiply the strontium isotope ratio with the strontium concentration of the source end member B, and in this we have to multiply with the strontium concentration of end member A. So, every time we use an isotope ratio, the concentration parameter also has to be taken into account. And when we are doing this concentration, it is generally the concentration that we have in the denominator. So, the denominator, whatever isotope is there, that concentration we are going to be using in the multiplication. We are going to weigh in that concentration. So, how will the equation be looking like? So, the first equation, as we write like a elemental mixing, we are going to write in terms of only one isotope, that is 87 strontium. So, let us write this equation with 87 strontium. So, how will it be? So, 87 strontium mix is equal to fractional contribution from this N member B multiplied with the 87 strontium of B concentration plus 1 minus Fb, that is basically Fa, into 87 strontium concentration of A. Similarly, I will write it for 86 also. So, I will write 87 strontium mix and I will write 86 strontium mix, and then simply divide equation 1 by equation 2. Okay. I will just take a ratio of these equations. Okay. So, 87 strontium goes on my numerator, denominator 86 strontium. So, this is my equations, how it looks like. Now, let us substitute using this assumption that my 87 strontium is equal to 87 strontium by 86 strontium isotope ratio multiplied with the 86 strontium concentration. Know the difference between the two brackets. When I am using this third bracket or square bracket, this generally refers to the concentration. Okay. This refers to the concentration. When I am using this second bracket, when I am using this curved bracket, then it means the isotope ratio. Okay. So, square brackets are always used for concentration and first brackets are always used for isotope ratio. Okay. So, therefore, if I do the substitution and I replace 87 strontium in this equation, I am left with this equation where 87 strontium by 86 strontium of mix is equal to Fb term plus 1 minus Fb into the A term divided by, again if you do that calculation you will reach this, divided by Fb if concentration of 86 strontium in B plus 1 minus Fb into 86 strontium of A. Let us now see how this is plotted. So, if we are going to use this against an elemental plot. So, what I am plotting is I am plotting 87 strontium by 86 strontium in my one axis and I am plotting another element. For instance, here we use neodymium, because as I have already discussed so many times, strontium and neodymium together gives the more accurate interpretation, because they behave oppositely. Because of their opposite behavior, specifically in the mantle processes, we use these two tracers specifically for understanding melting processes, petrogenesis and mixture of different kinds of rocks if we are looking in aquatic systems. So, let us, if we use this and we are plotting against the elemental concentration, that is neodymium, complete neodymium concentration. So, if we plot this, we are going to see that we are going to get this particular equation where we have a term with 87 by 86 strontium, we have a term with neodymium mix, we have another term with just neodymium mix and a constant term. So, we are going to solve for that parameter called fractions, because we have to find out how the Fb comes. So, we cannot incorporate Fb in the equation, right. We cannot put Fb in the equation. Using the data, we have to find our Fb. So, you have to eliminate Fb from the equations, and when we eliminate from the equations, we come to this big equation. And here what does these coefficients mean? So, A is this term, B is this term, C here is this term, D here is this term, right. And you will see that now this is in the form of the equation Ax plus Bxy plus Cy plus D equal to 0. And one more important thing that I forgot to mention before is that here we approximate we do an approximation with the strontium concentrations. For instance, if you are taking the strontium concentration, here we need that strontium concentration of 86 strontium, but we are going to assume that whatever we are measuring as a strontium concentration is equal to the 86 strontium concentration. With this assumption, all our equations becomes very simple to deal with, because here now we are dealing with only the concentrations and not the isotope concentrations. So, this is a small assumption or approximation that we make, and you will see that this approximation works very well. That is why it is practiced, because when we are doing real life measurements, we see that it is working pretty much fine given the acceptable errors. So, with this equation, if I plot, that is Ax plus Bxy plus C equal to plus D equal to 0, what kind of plot will I get? I will get this kind of plot. And what is this? It is a hyperbola, right. So, we will get a hyperbolic plot when we plot this 87 strontium by 86 strontium in one axis and neodymium concentration in the other axis, right. So, the only case that this kind of mixing of a ratio and an element becomes linear rather than a hyperbola is when this B term equals to 0, right. But this is very rarely it happens that the B term becomes 0. And one more important thing is the radius of curvature. How much is the radius of curvature, or how hyperbolic is the hyperbola, you can find out with the strontium or by the ratio of one of the tracers given the end member values. Another kind of mixing is when we have a inverse element and ratio. So, we just looked into where we plot an isotope ratio in one axis and the element in the other axis. So, in this third type of mixing, we are not going to plot A by B versus B, we are going to plot A by B versus 1 by B. Okay. So, by 1 by B I mean, for instance, we were plotting 87 strontium divided by 86 strontium versus strontium if we were going to plot. In this case, we are going to use 1 by strontium. Okay. Then if we replace all these terms, okay, of neodymium with 1 by strontium and we again solve this equation, then my A term comes to 0, my B term is this, C is this, D is this. But now since this A term becomes 0, my equation now becomes this, which is a line. So, it is in the form of y is equal to mx plus c, right, y is equal to mx plus c. This is how it becomes, and when I try to plot it in the graph, so given this is my y axis and this is my x axis, I will see that now it falls on a line. The mixing shows me the line and the end members will always sit far from that line, and this is how the mixing will look like. So, the value of r, so the distance or the spacing that we say of every increment. So, the spacing of increment now depends on this r. So, this is that curvature of the hyperbola that controls the spacing of the equal increments of mixing, and you will see that it is not a linear mixing, right. It is not a linear mixing, because linear mixing becomes very easy to calculate. So, therefore, now this kind of the distance between the mixing now depends on this particular value, that is the strontium ratio of the two end members. Okay. So, this we have to test whether it is consistent with the binary mixing than in the ratio element space. So, we have to test that using both. So, the strontium isotope ratio and both with 1 by strontium. So, both we have to check and see whether we have an n member mixing, which is showing us this kind of mixing, or whether it is due to another n member. The last type of mixing ratio that we are going to understand is the mixing between two ratios. So, here we have seen one isotope ratio and the inverse of an elemental concentration. In the fourth type, we are going to use both the tracers as isotope ratios. Okay. So, here both my tracers are two different isotope ratios and their mixing equation will be in the same form. Okay. Here again we are going to make this small assumption or approximation that whatever is the denominator isotope ratio, that will be my complete elemental concentration. That is, if I am using 86 strontium as the denominator, that concentration is my total strontium concentration. If I am writing 144 neodymium concentration, that is equal to my neodymium concentration. With this, if I am trying to find out for my FB, that is I am going to eliminate my FB and I am going to write the equations now solving for FB, then my equation becomes this equation again. Okay, where the A term is this, B term is this, C term is this and D term is this. So, you can see it is a pretty big equation, due to which the terms has been substituted with this A, B, C, D coefficients. Okay. And again it gives us the equation of a hyperbola, and this time the B term gives the curvature index with R equal to strontium by A divided by strontium of B, the whole divided by neodymium of one n member A divided by neodymium B of the other n member. So, this is how we are going to solve for the FB term, and we are just simply going to plot both the isotope ratios. As you can see in this space, we have plotted, and this gives us the hyperbola. And as you can see, the spacing again is different, the incremental spacing is again very different. So, 0.1 fractional contribution from A. So, this is 0.1 contribution of FB and 0.9 contribution of FA, but it is sitting right in the middle of the curve, right. So, here you see if you change the additional contributions, it is the FB term is moving closer to the B axis here. The incremental distance is very, very less. So, this kind of unequal incremental spacing we have to be very careful about if we are depending on the data to fix our n members. So, it is always recommended that we go for the more linear mixing plots. We try to make the plots more linear, because this kind of index of curvature we will not know how the how the incremental spacings are if we do not have the n member values. Because if you know the n member values, then it becomes very easy, because you simply know the n member mixing value, you can find R, you will know the incremental spacing values. But if we do not have the first hand information of the n member, then it becomes very difficult. If you are using the data to show the n member values, then it becomes very difficult. So, whenever you are trying to find out from the data of the n member, then we are always suggested to use the linear plots. Always suggested to use the more linear plots. And here just to show you an example how different it can be. So, here if the R value changes, then you see, so R value equal to 1, then you have the linear curve, a straight line. If the R value is changing to 3.75, you have this kind of curvature. If the R value shifts to 10, you have this kind of line. If the R value is 1000, just this kind of curvature. So, depending on the R value, you can have this or this kind of curvature, right. So, understanding this curvature is very important for you to correctly do the mixing calculations. So, either then you know the end members and you very correctly identify them, or if you do not know the end members, then you go for a more straight line mixing model that does not depend on this R. So, often we are going to see these kind of plots where we have either elemental axis. So, there are two elements on the two axes. For instance, here as they have plotted neodymium versus strontium, or you plot the same elements. So, 87 strontium by 86 strontium by strontium or with 1 by strontium, and you can see this and this, these two types of plots are the most preferred types of plots, where you can have the two end members and their incremental depends on the end member strontium values. So, with this, if we are doing this kind of mixing where we are trying to understand what are the source contributions, then these are the most preferred types of plots. Okay. With this, we come to the end of this lecture, that is related to mixing theory, and in our next lecture we are going to move towards the next module that deals with stable isotopes. Thank you.